This is a hologram. Holograms have little in common with traditional photographs, except that both use film. Holograms can create completely three-dimensional pictures, and every piece of the film can reconstruct the entire image. In order to understand holography, you have to understand something about waves. When waves meet, their effects are additive. When two crests meet, we get an increased effect. But when crest meets trough, their effects cancel out. This interference effect is important in holography. Here are two random sources of waves, not of equal amplitude or frequency. If we make a time exposure of their shadows, the image is completely washed out because nothing remains in place. Here are two pure wave sources of equal amplitude and frequency. Notice the areas of motion and calm in the water. A time exposure looks like this. As long as the frequency and amplitude of the two sources are constant, an interference pattern will be formed wherever they cross. These two speakers send out pure sound waves of identical frequency and amplitude. The microphone records areas of calm and motion. If we could see the three-dimensional interference pattern caused by the two sound sources, it would look like this. Light also travels in waves. What happens when two light beams cross? Interference of light waves should produce bands of light and dark, but we see none. In general, when two white light beams cross, no visible interference pattern is produced. A red filter will help to make the light monochromatic. Even this highly filtered light, however, is not monochromatic enough to produce a noticeable interference pattern. Let's examine the light source. While our water and sound waves are in step with one another, the light bulb produces light of many wavelengths, which are not in step with one another. This is the inside of a laser, a source of intense and spectrally pure light. The laser emits light waves more monochromatic than any filtered light source. We will use a laser to check for interference by passing its light through this optical device, which splits the beam in two. The interference should appear as bands of light and dark. Here is another demonstration using laser light. A partially silvered mirror allows half of the light to pass through while the rest is reflected. Where the two beams of light cross, we will place a film. Notice the camera has no lens. It is simply a film holder. This will be the path of the light. The film looks blank. But watch what happens when we remove the beam splitter, leaving only a single beam of laser light. The film reconstructs the original two sources from only one beam. How did this happen? Within the film emulsion, areas are exposed as light waves move through. Where the wave fronts cross each other, the silver emulsion is exposed. The developed emulsion is essentially a thick diffraction grating. Here is a microscope view of the processed film. To understand holography, we can think of the developed layers within the emulsion as a set of microscopic, partially reflecting mirrors. This film was exposed with two beams, interfering with a third. Now, by passing one beam through the film, the two other beams are reconstructed. If this car were illuminated with a laser, every point on it would reflect some laser light. This is how a hologram is made. Part of the beam is used to illuminate the car. We'll call this the object beam. A second beam, called the reference beam, shines directly on the emulsion and interferes with the light reflected from every point of the car. The exposure must be made on an absolutely motionless surface. Even the slightest vibration will ruin the hologram by smearing out the interference pattern. We will expose the film for about 10 seconds. The film looks blank, but through a microscope we can see interference patterns which bear no resemblance to the real car. Now, when the reference beam alone shines on the processed film, an identical image is reconstructed. Here is an explanation of what happened inside the emulsion. The reference beam from the left interferes with each reflected light beam from the car, creating an interference pattern. The emulsion simultaneously records all the patterns caused by all the points. Now, when the reference beam alone shines through the film, each pattern reconstructs its own object beam, and thus the whole car appears to be reconstructed. What would happen if the emulsion had been here, between the source and the object? In this case, the interference produces what is known as a standing wave pattern. These are standing waves. Therefore, if the light shines through the film and reflects back from the coins, there will be standing waves of light set up in the emulsion. Laser light will shine through the film and reflect back from the coins. An ordinary white light is used to view this hologram. Why does white light reconstruct this kind of hologram? A cross-section of the emulsion looks like this. White light approaches and passes through the film. The mirror planes are spaced to reinforce only the wavelength used to make the hologram. Because the film shrinks in processing, the green color of shorter wavelength is reinforced rather than the red. Here is another white light hologram. When a laser shines through a hologram and onto a screen, a two-dimensional image is projected. Even a small fragment can project the entire image. Holography is an efficient data storage medium, which may soon outdate traditional microfilm. Here is a two-channel hologram. Two scenes have been recorded at different angles on the film. The channel is selected by tilting the film. The lens in the holographic reconstruction actually works. This is the principle used in microscope holography. A slide is placed in front of the final element of a microscope. Later, movable lenses will be able to act with the lens in the hologram, allowing us to selectively focus on any point within the slide. Through holography, structural flaws can be seen in solid objects. The dark lines show a stress pattern. By aligning the real object with a hologram image of it, a tap of the finger can be shown microscopically bending the steel. This circular hologram was made by surrounding the object with a strip of film. There are an increasing number of practical laboratory applications of holography. Here, the effects of heat are made visible. Even very subtle heat effects are clearly visible. Holography is in an early stage of development, similar to that of photography 100 years ago. Yet already artists have found in holography a new medium of expression.